Okay, I think we can start now. People will probably pour in during the presentation, so I'm recording it to the cloud so we can all watch it later on. All right, so first of all, thank you for joining. We have Sebastian here with us. He's the business development lead at AWS Quantum. And Sebastian, why don't you tell us about yourself in a couple of seconds, and then we can move into the presentation.
Yeah, absolutely. Thanks so much. And thanks for everybody for having me here. I joined AWS in September of last year in a business development role, and I'll get into more about what we're doing at AWS later. I was actually at IBM in the research department looking at quantum computing, working in the quantum team for about 3 years prior to that. I started my career, I've always looked for sort of emerging technologies. Started my career in IT in the mid-90s. I joined Apple and built their first customer support website in very early days of the web. We were briefly in the top 10 most trafficked websites in the world. One of my claims to fame. I think it lasted about 6 months, and then there was another 500 websites and we were knocked out. From there I went to IBM. Actually, it was my first stint at IBM. Where I worked on product strategy around mobile computing, everything from handheld devices to computing in cars, RFIDs, all sorts of and early days of IoT, all sorts of sort of new capabilities that were possible as the computation shrunk and the resources got more powerful. And then I went on to do a few different startups. One was building mobile development or mobile apps in Vietnam, actually based in Vietnam, the team was. But that was on a for-hire basis. And also, I joined a startup that was building a robot that brewed beer. So I've had a very wide range of experiences. I really love quantum computing because it's not just an incremental enhancement of the existing technology. It's not, mobile. You could say a smartphone is like a special kind of PC. A laptop is a smaller kind of PC that we've been incrementally improving computation capabilities for 70 years. This is an entirely new type of computation, entirely new technology that's just starting to emerge. So there's an enormous amount of exploration to be done, and that's the kind of thing that motivates me as a technologist and as an entrepreneur, frankly. So I'm very excited to sort of delve into this and give you guys a view of what it is, what the state of the technology is today, what AWS is doing with it, and what we see as the sort of landscape in the scientific and technologist and business kind of perspectives. So I will share my screen. This can be as interactive as you want. So I have slides that I'll go through. Can you see them now?
Yeah, I see them.
Great. But at any point, just let me know if you have a question. I'll try to leave pauses to make sure that I don't talk over everybody's questions. I tend to talk quickly. So first of all, what is quantum computing, right? So what do we mean by quantum computing? This is a new class of devices that are the beginnings of the practical realization of about 30 years of theory. So back in 1981, MIT and IBM had a conference actually at Endicott House where a number of physicists and computer scientists got together and discussed the possibility of using quantum mechanics to do computation. And Richard Feynman, who's quite famous even at that time, delivered the keynote. At the keynote, he said, "Nature is quantum by nature, so or by its its intrinsic properties are quantum, and therefore, if you want to simulate nature, if you want to understand nature, you're going to need a quantum computer to do it." And that really kicked off 20 or 30 years of theoretical work to figure out, how would you do that in theory. In the late 90s and early 2000s, the engineering started to get caught up with where the theory was. And we started to implement actual qubits, the quantum bits, or the unit of quantum computation in a variety of different ways. They were early stage then. They still are early stage, but they proved that the theory was not just theory. That it could be practically realized, and that sort of really reignited the interest in the field, I would say, especially when IBM put the first quantum computer on the cloud in 2015. And now there are a number of vendors who have a number of different types of machines. All of this is because the theoretical promise of quantum computing is that for certain types of problems that are very, very hard for classical computing, quantum computers can do them in a matter of minutes. So not an incremental increase like even a 10x performance, but a performance of 10 to the x. So a completely exponential or quadratic explosion in terms of performance for certain types of problems, especially scientific and engineering problems. So things in natural sciences, physical sciences, back to Feynman, things that are attempting to simulate nature. But at this stage, we are in this era we call NISQ, noisy intermediate scale quantum, which is very interesting from an exploration perspective. It really, the machines we have today don't offer any advantage over classical computing. So that's the first sort of headline that needs, or bubble that needs to be popped, is that while it is incredibly promising at this stage, it is a research technology. So anything you can do on quantum computers, almost anything you can do on quantum computers, you can do more easily or more performant on classical computing. But it's the nature of this technology is so promising that it makes sense to start investing in and understanding and exploring the possibilities now, because it will be such a disruptive technology.
I think we have a question from
Yeah.
Vikram. So
Yeah,
go ahead.
yeah. So I just want to understand, is it about hardware or is it about software inside the computers? What is making it faster? Yeah.
So it is hardware. So, in a classical computer, you use transistors on silicon to do Boolean math, right? You're doing all ones and zeros, basically. And when you render problems in Boolean math and in Boolean algebra, certain types of problems become exponentially harder. It's a very good segue to this slide, actually. Thank you. So some problems become exponentially harder as you add more variables. And that is typically the case in simulation of nature and other types of problems that are multivariable in nature. So that's Boolean logic, that's classical information technology. Quantum information technology, the qubit actually is capable of not just a simple 1 or a 0, but actually some probabilistic combination of those two states, of the 1 state and the 0 state. Through very complex quantum mechanics that I frankly don't have the PhD to understand in detail. I understand conceptually, but what the net of that is that the math, the type of math that is natively supported on the hardware is linear algebra. Which makes these classes of problems more tractable. And I'll give you an example. I always found the traveling salesman problem the easiest to understand because it's a fairly well-known problem. It's a salesperson needs to make calls on X number of cities, and the problem is what's the optimum route for that salesperson to travel, the minimum distance to visit all of those cities. There's no efficient way to solve that problem in classical computing. You have to experiment with almost all of the combinations. You can eliminate some of the obviously wrong ones, but you don't have a really good algorithmic way to tackle that problem. And what's worse, every time you add another city, you've doubled your problem space, right? At least you've actually added an exponent more numbers of combinations that you need to test. With quantum computers, you're actually able to model that using math that only scales linearly when you add another city. So in other words, if you have n number of cities, you'd need 2 to the n bits to represent all the possible routes. With a quantum computer, and then when you add one more city, you need 2 to the n plus 1, so you've actually doubled the number of bits that you need to represent it. With a quantum computer, you need n qubits, and if you add a city, you just need n plus 1 qubits. And that's theoretical because we're still working on how to do that in practice, but conceptually that gives you a really good idea of how this curve is possible, right? In classical computing, that number goes up in an algorithmic or an exponential kind of way. in quantum computing, those problems scale linearly, and therefore are much easier to solve. So, where are these types of problems found? I mentioned nature, chemistry, and material science in particular are the areas where we expect the first commercial applications to emerge, most likely. Reason being, when you're simulating a molecule, it's very similar to that traveling salesman problem in that every electron orbital affects every other orbital. So if you're trying to simulate a molecule with 10 orbitals and you add one more orbital, that's now 2 to the power of 11 number of qubits you need bits you need to represent that simulation. With qubits, you're actually modeling each qubit is an orbital. So you just need to add one more qubit and you can model that whole orbital. Similarly with materials, you're doing the same sort of thing. You're simulating the material characteristics or the characteristics of a molecule that makes up a material. So that's probably going to be the first sort of class of problems. Machine learning, there's some early indications that we may see some great advantages from quantum machine learning. This is in the class of what I would call variational, and I'll expand on that later. It's actually combining classical computing with quantum computing, and the approximations. When in machine learning, you're often taking a model and approximating a solution, and then testing that approximation and adjusting your next guess at the solution. Coming up with that approximation is actually something that's very difficult for classical computing, and it's very easy for quantum computers. So you're able to. Oh, go ahead. Was there a question? Okay. So in that case, you're able to sort of pass your problem back and forth from the classical computers to the quantum computers. And in conjunction, they can potentially deliver faster performance than just classical. And then in the optimization class, that's a pretty broad set of problems. Logistics in general, that's where the traveling salesman problem would fall into that category. But it's definitely seems to be applicable to any type of logistics. So, whether it's transportation or shipping or QA processes or anything where you've got a process that has constraints around time or distances or number of nodes, that sort of thing. That may be another area where there's some early. In fact, some of the earliest attempts to show commercial advantage with early quantum computers in the 90s that were not universal quantum computers, but they were annealing machines. They're from a company called D-Wave, which we have on our service. They're still around. They are geared specifically towards these optimization problems. Okay, so at AWS, we're making a very serious long-term investment in quantum computing. I keep saying it's very early days, but we have committed to quantum computing in a very profound way with these 3 distinct efforts that my group is actually sort of the only one that sort of spans all 3 of these. So there's a team building Amazon Bracket, which is a quantum computing service. It's part of the AWS cloud services. It is fully integrated with the rest of the AWS portfolio, and it provides access to multiple hardware backends. So it's one unified interface for writing software that will run on different types of quantum computers on the back end. We have on the far right, we have the AWS Center for Quantum Computing. This is a new facility that we've just finished construction on and officially opened in, I think, October of last year. It's on the Caltech campus, and that team is actually building our own qubits as well as doing applied R&D into other hardware questions around error correction and that sort of thing. So sort of fundamental research challenges. So we're building our own qubits as well as putting other vendors' qubits onto the service, in part because it's anybody's guess which type of qubit is actually going to succeed, and also because we believe that it makes us a better partner to our quantum hardware vendors, that we understand how difficult it is to make these machines. They're extremely challenging. And we're better able to support our partners' efforts by understanding those challenges firsthand. And then the Quantum Solutions Lab is a professional services team. These are specialists in quantum computing, quantum information science. They engage with our large enterprise customers to help them fully understand the dynamics of quantum computing. Where is it today? What skills are needed? Making them quantum ready, and looking at their business processes and trying to figure out where quantum may have an impact in the near term, and how to help that customer get ready for that sort of coming disruption. In addition, they often will build out classically powered solutions where there's a very large HPC or high performance computing cluster that's standing in for the qubits. So, there's sort of an end-to-end solution. It delivers some value to the customer, and it's architected in such a way that when the quantum computers become powerful enough, they can be substituted in for the classical high performance computing when that actually provides more of an advantage.
Sebastian, a question maybe about this one. So in terms of the organizational structure, so AWS treat each of these parts as a separate vertical?
Yes.
So isn't there like a concern about cannibalization of your qubits for the Amazon bracket service? Because eventually,
it's a good question. Right, it's a good question. We don't really worry about that, because even in classical computing, as mature as it is, if you look at EC2, which is our cloud compute resource or service, there are Intel chips, there are AMD chips, there are NVIDIA chips, there are FPGA chips, there are Amazon chips, right? The Annapurna Graviton, the Annapurna acquisition, which has led to the Graviton family of chips. So it's really driven by, yeah, that's right, exactly. It's driven by customer demand, and what we're nearing the, we've been saying this for years, but everyone says that Moore's law and that pace of improvement of classical can't keep up on the same architectural path. And I would say that we're already seeing a response to that in the fragmentation of the compute landscape into all of those chips I just listed off, right? You wouldn't need GPUs if CPUs could do a better job of those types of workloads in graphics and machine learning, right? So we're already seeing this heterogeneity in the compute landscape. We expect that to continue, and actually you'll see when we get to the hardware backends, there's already a large amount of heterogeneity, and there's no signs that that's going to end anytime soon. So, as I said, it's really a matter of customer choice, and the net benefit to our hardware partners for us knowing how hard it is to build these systems and being able to build Bracket in a way that helps them get online and helps them mitigate some of those complications of getting hardware or building quantum hardware is more important to them than any kind of potential perception of risk, I think.
All right.
So with Bracket, this is a service that provides a single interface for accessing quantum computers, for running circuits, and also for running circuits on simulators. So we have a number of managed simulators in the cloud that can use classical hardware to simulate up to about one simulator goes to 34 qubits, another one goes to about 50 qubits, which is, it's enough to test out theories and algorithms, but obviously the performance is limited by the classical hardware. It's not going to give you a better performance than that. Back to the question of whether this is software or hardware. Without the hardware, a simulation of qubits is not sufficient for gaining that advantage in performance. So that's the Bracket service. At a high level, this is the way it's architected. I mentioned it's a fully integrated service along with the rest of the AWS services. This is a huge advantage, actually, because as customers start to try to understand how quantum compute will impact their workloads in the future, they do that in the context of the rest of their cloud compute infrastructure, right? So if they have existing HPC solutions, like I was mentioning before with the Quantum Solutions Lab, they can set up test instances of those HPC solutions in the cloud and substitute in a quantum simulator, for example, to see how that affects the design, the architecture, and the design of the end-to-end solution. Or they can use data that's already in the cloud. They can use all the same security and management capabilities. So it takes a lot of the obstacles and barriers to entry out of the way by having this a fully integrated service, even though it is such an early stage.
And
Yep.
just about the infrastructure, how much of the Amazon bracket that you see in the middle, how much of it you just directly inherit from the already existing cloud services, and how much you had to like specifically
That's a great question.
and tailor for each and individual hardware vendors?
Yeah, it's an excellent question. So there is the managed environment for Bracket in the cloud is based on SageMaker, which is our machine learning managed notebooks solution, our service. So we did inherit a lot of the notebook interface and the management of resources from SageMaker. But the integration of each hardware provider and each hardware device is somewhat of there aren't standards yet, really. There's one standard called OpenQASM or Open Quantum Assembly Language, but in many ways that's just a simple interface. So each of these devices comes with its own challenge, and the Bracket team is working with each hardware provider to get its particular device online. And I'll talk a little bit more when we get into the details on the hardware about some of the variations there. But it's a really good question. So in fact, IonQ and Rigetti are both what we call gate-based quantum computers. So they both have a universal set of gates in the sense of like a Turing machine, of like a information science kind of perspective, and they can take the same circuits and compute quantum software essentially in roughly the same way. Now, they are two different kinds of qubits, and that's the heterogeneity I was referring to before. Rigetti is an example of a superconducting qubit. So it's actually in the bottom of one of those big cylinders you may have seen pictures of. It's a dilution refrigerator. It drops the temperature at the bottom of that fridge down to about 14 millikelvin or 14 thousandths of a degree above absolute zero. And it uses a superconducting circuit to make this quasi-particle that exhibits quantum behavior at a macro scale. So that it makes it larger so it's easier to manipulate and read. It's very fast performance. It's the same type of qubit that IBM is building, that Intel's building, that Google's building, and that AWS is building. IonQ is an example of a trapped ion qubit where there are individual ions that are trapped in a vacuum chamber and then manipulated with lasers instead of electromagnetically. It has the advantage of not needing to be chilled down to extreme temperatures. And in other words, it can be potentially rack mounted. They're building devices that will be able to go into regular data centers. There are other vendors who are also building these. Quantinuum, which was Honeywell merged with Cambridge Quantum Computing, Alpine, and IQM, I think, which is a Finnish company, among others. So these are two very popular approaches today. Trapped ions have a lower error rate, but a slower performance, and superconducting have higher performance, but higher error rate. So they each have their own engineering challenges. D-Wave, as I mentioned, is that does not have a universal set of gates. So it's more of you can think of it as more of an analog device. It actually does what's called annealing. So it's very well suited to optimization problems that you can formulate in a way that that mathematically the D-Wave can solve. So that's also a very popular device in the system. We're adding another superconducting device, this Oxford Quantum Circuits, which is the first device out of North America. It's actually in the UK, as the name might suggest. It's a spin-off from Oxford University, in fact. It's also superconducting, but it has a different architecture. So even when you say superconducting, each of the vendors who are making superconducting qubits are approaching it in some sort of either subtly or radically different way. In the sense that in the case of OQC, they're doing interconnects at the top and bottom of the chip, which they think has significant advantages to the standard way of doing superconducting qubits. And the Quera device is a spin-off from Harvard, Misha Lukin's group at Harvard. It's a completely new type of qubit, which is an array of neutral atoms. So it's 256 Rydberg atoms in an optical array. There's lasers that are holding those atoms in an array and that are manipulating them in that array. And why I mentioned this in detail is that you were asking, how does the integration work? This is another example of a device that does not have a universal set of gates. So yet they're working on that, but it has value as an analog device right now for simulating Hamiltonians, which are a way of representing natural systems. So when we launch this, it'll actually have 256 atoms that are available to do analog Hamiltonian simulation, which is a completely new type of quantum computing to be available in the cloud. So that's the kind of sort of radical innovation that's still happening on a quarter by quarter basis, and that requires a lot from our service team to accommodate and to integrate. These are the managed simulators. I won't go into detail on them. It's just to suffice it to say that in the typical sort of life cycle of any experiment, the researchers will work on formulating a problem probably on paper on their laptops, and then they'll try formulating it in the form of a circuit, test it out on simulators, and then once they want to get results from real hardware, they can just change the target for that circuit to a piece of real hardware and run the exact same code. So it has the advantage of being sort of transparently integrated with the Bracket service, and these are actually, I think, oh no, never mind. These I'll get to pricing later on, but these are charged by, like any other AWS compute resource, they're just time-based charge as opposed to the quantum hardware, which we'll see later is a little bit more complex. So the current state of exploration, I would say there's sort of three areas that map roughly to what I was showing at the beginning of the physical sciences, the quantum machine learning, and the optimization problem. So these a lot of those are addressed with these hybrid classical quantum algorithms, right? There are examples of things where the code is being passed back and forth between or the problem is being passed back and forth between classical code and quantum code. We have a feature that we just launched in December called Hybrid Jobs, which actually allows you to containerize your classical code and run it right beside the quantum computer in terms of the infrastructure. So there's a very, very low latency in that loop, and you can iterate back and forth between classical and quantum without any other job getting in the way. So you can do quite sophisticated workloads in this way. Now, this is still exploratory, just like everything else. So you'll see mentions of hybrid quantum classical in a number of different realms. It's still indeterminate whether any of them are going to get to the point where they actually offer some sort of performance advantage. But there's a lot of very interesting research that's going on using these types of approaches. I mentioned quantum machine learning. One of the leading libraries for quantum machine learning is PennyLane from Xanadu, and it uses a lot of these hybrid approaches. I mentioned the approximation step happening on quantum computers with things like state vector machines. PennyLane is from the Xanadu company. They're a very close partner, and we've integrated PennyLane directly into Bracket. So I mentioned this as an example because there's a very large and vibrant sort of community of open source development going on, and PennyLane is an example of that. We're integrating into Bracket. So we're really seeing Bracket as an interconnection point for all that hardware on the back end, and also sort of all the wealth of open source and commercial software that's being developed on the front end. There's a ton of tutorials and examples for those of you who either are interested in getting deeper into it or know someone who might want to get deeper into it. And there's all kinds of resources for supporting research as well. I've got quite a large fund of credits that I can use for academic research, and we also have partner programs for startups and ISVs to be using Bracket for they're building out their software as well. I mentioned pricing. It's just to touch on this because it's a really interesting, for one thing, it's we've actually unified the pricing model. We apparently were the first company to actually price out quantum computing as a service on the cloud, because the vendors themselves, who often have direct relationships with their customers as well, they were operating on different types of models, not consumption-based, pure consumption-based models. So when AWS set out pricing and launched Bracket in, it was about a little over a year and a half ago now, summer of 2020, I believe. The public pricing was the first time that quantum services had been actually priced out in this way. And you can see there's uniform per task pricing, but each task, that's any given circuit that you're going to run on a quantum computer. You're going to typically, quantum computers are probabilistic, so you're going to need to collect a data set of a number of runs of any particular circuit, right? So you'll do 100, what we call shots, or 100 or 1,000 shots of one particular task. So there's a flat price for the task itself, and then there's a variable price for the number of shots you have to actually do to gather that data set. And you'll see differences in the way the hardware works is reflected in that per shot pricing. I mentioned trapped ions are slower but less error prone, so their per shot price is actually higher than the superconducting, which is able to perform more executions per second, but ends up with a higher error rate. So you need to have a bigger sample of your problem set to actually get a good result.
So actually, the price here is something that was set by the hardware vendors, or is it something that you decided upon, or is it kind of some negotiation that went?
Yeah, well, we had the tenet that our customers wanted as uniform pricing as possible. So we went into this, it was a multi-party, we were negotiating with each of these hardware partners, and all the hardware partners we're talking to now about adding future hardware. There is, obviously, you need to come to mutually beneficial business terms. We did go into it saying we wanted to establish one, as common a pricing unit as possible. So that's where you see that uniform per test price, and we'll stay to that. We'll stick to that as much as we can. There may be, instances in the future. We're already talking about potentially use cases that drive time-based pricing instead of task-based pricing. So there's certain use cases where task-based pricing doesn't make as much sense. So we may introduce variations to this in the future, but we're going to try to continue to keep it as transparent and uniform as possible, because we feel like our customers really, they've been telling us that they want that. It's hard to figure out what something costs in the quantum computing space. So we wanted to help them with that. Where you'll see the variability is, as I said, on that per shot price. So the hardware vendor has more flexibility on that pricing. And it's based on the characteristics of their hardware. So that's where a lot of the variability comes in.
And see, Vikram, you have a question?
Yeah, I was wondering, because the whole solution is offered by Amazon, so what incentive these hardware vendors have to develop quantum qubits? Because ultimately they will kind of become a commodity, and maybe their all efforts, this is kind of R&D, and they do an R&D and they don't get anything that may happen. So what is their motivation?
Yeah, it's a really good question. I don't think that that being available on the cloud is necessarily going to drive them to commodity. I think that, again, this isn't classical computing 2.0, right? It's a completely new paradigm. So we really don't know how the value chain is going to develop. And there's a lot of speculation from different quarters on how that might happen. But if you just take a quantum hardware provider today, they have an enormous engineering challenge, enormous scientific challenge, a number of them actually, to make qubits that work better than their competitors, to differentiate themselves. They don't really want to be in the business of building a whole cloud infrastructure as well to build their own digital route to market, right? So the relationship with AWS provides them with access to developers and researchers who can take advantage of their qubits and can collaborate with them through that use to help them understand how to make their product better. So there's more advantages to a quantum hardware provider in being on AWS's cloud than not, in my view, and in the view of the hardware providers have joined. It's very, very difficult to innovate in a vacuum. You need to have users to make a product better. And the reality is that the cloud is, dominated by a few very large players, and you need to go to where the developers are. So we again, like the value capture is something that is sort of uniform across our different services in the classical space, right? That's something that we have to come up with terms that are beneficial to each of our partners who are providing. I mentioned NVIDIA before, right? They've got a lot of ways to get to market, so we have to be a good partner to them. And make it a mutually beneficial relationship. The same will hold true in quantum, and with the extra proviso that no one really knows where the advantage is going to come from. It may be that there's some completely unexpected innovation that comes, and a new class of service is born out of that innovation that is driven by a quantum hardware provider. We would be delighted to sort of reset the relationship and figure out how to surface that value for our customers in collaboration with that innovative partner at any point in the future. I mean, the reality is that no one knows where this is going or where the sort of decisive, I've been doing a lot of reading over the last number of years about the origins of the classical computing era and technologies. And right now I'm reading a book called Turing's Cathedral, which is about the machine that was built at Princeton at the Institute for Advanced Studies, actually with quite a bit of input from Norbert Wiener from MIT at the time, who's sort of considered the father of cybernetics. And the reality is that that's really the stage we're at in many ways, right? That we're building these one-off machines like ENIAC, like there were a ton of other funny acronyms, Johnniac, Maniac, that were built in the 40s and 50s and early 60s, that were exploring how to make these machines and what they were good for. And no one could have possibly foreseen the personal computer, let alone the web or the iPhone at that point, right? Or like shopping on the phone or dating apps or whatever. So that's really the stage we're at right now. It's wide open exploration and I think a very open mind about where the innovation may come from and how it will be. How it will be realized and how to bring that value to customers.
One more question,
Yeah,
because you have already started selling this service. So I am just wondering, because you said that this service is like not better than, even you are speaking about errors in the solution, like maybe computation, which possibly in classic computers doesn't happen. I have not yet to see that some producing error in the computation. So are people buying this service, and then if yes, then why?
An excellent segue to this slide, actually. People are using the service, and people are, obviously, there's an enormous amount of interest and excitement about quantum computing, even at this early stage. So, the goal of Bracket is really not primarily to generate revenue. There isn't enough economic value represented in quantum computing today to, even if we captured 100% of the market, it wouldn't make that much difference to AWS as a large as an entity, right? The Bracket and the quantum efforts are an investment in understanding how the technology is developing and helping our customers understand, because there's a very strong argument, because this is, really at its roots, a different way to look at and identify problems, formulate those problems, formulate the solutions, test those solutions. It's not a matter of porting existing algorithms over to quantum computers. It's really much more exploratory than that. And it requires specialized skills. It requires a different way of looking at problems. And it requires a whole host of other sort of capabilities and activities and institutional knowledge that we sort of collectively call quantum readiness, right? So, the scenario that a company wants to avoid, let's say they're a bank, right, and they're a financial services institution, and suddenly there's a quantum advantage in one of their lines of business, and they don't have the 5 or so years of investment of time in having that expertise ready to go. That's 5 years of an potentially exponential speed up or exponential advantage in that line of business. That's going to be very hard to catch up with, right? So there is definitely a very strong motivator to be, at least ready, if not being the one who's actually exploring those potential applications. Like, there will be huge advantages to people who find those initial applications that do drive some kind of economic commercial advantage out of quantum computing. Does that help?
Yeah, thank you.
Sure. And so that's actually a great segue as well into, we do have a large and growing ecosystem of partners. So there's a whole Build on Bracket program, which provides ISVs with support and resources for building their startup software offerings on top of Bracket. The advantage to them is that up until Bracket was launched, they had to make relationships and deals individually with each of the quantum hardware vendors that were making their technology available, and then maintain those relationships and maintain separate and distinct interfaces. Each vendor had their own flavor of integration, their own set of APIs, their own integration model and programming model. So that would be compounded with the number of hardware platforms that they wanted to support. With Bracket, they can build to the one Bracket service and access all of the hardware that's available in one place. So those examples of that are Blue Cat, which is a chemistry startup out of Japan, QCware, which actually has a whole platform that runs quantum algorithms across a number of different solution areas, Zapata, which is also focused on chemistry, Q&Co, another chemistry, Qsimulate, another chemistry. There's a lot of activity in the chemistry space. Multiverse is more financial services. I believe Rocco is also, there's a few, this is actually a little bit old. There's a few newer ones which are more focused on financial services. And then there's the there's a number of consulting companies. See, One Qubit would be the example here of consulting, which is sort of expanding that mission of problem identification and problem formulation that I described before, helping companies be quantum ready. And this number is expanding all the time. I think that it's a testament to how vibrant and how exciting the technology is, how vibrant the startup community that's building up around it is, even at this early stage. That this community is growing quite large, quite quickly.
From like your business development perspective, there are a lot of startups, a lot of companies which join this ecosystem. Now, when you want to onboard them and bring them to Amazon Bracket service, for example, do you just go for the grab? Do you just try to get the market share because you don't want, let's take Amazon, Microsoft Azure to get them, or is there like a deeper set of considerations?
I see. Yeah. So it's a really good question. This recap, the first bullet here, democratize quantum computing. What we mean by that is really for everyone, for the end users, as well as the hardware providers who are getting access to a very large number of potential users by integrating with Bracket, as well as with the ISVs and the SaaS offerings. So they can actually have focus on their differentiation, which is their software implemented, their IP in the software space, and not on the cost of integrating with multiple hardware providers and maintaining multiple hardware interfaces. So, the larger point that we sort of are making here is that with so much innovation required to make this useful technology, it really makes sense to collaborate as much as possible. So bringing all of the scientists and the engineers who know how to build these devices together with the researchers, the information theorists, the computer scientists who are exploring how to use these devices, and the end users who will be consuming the services and the value that is created on these devices. Bringing all those people together in a large sort of collaborative group is only going to be good for the field, right? The field needs a large number of scientific and engineering breakthroughs to become really viable, and to start to realize all the promise. And so innovation, it's been, it's a proven model that the more you openly collaborate, the faster your innovation will be, right? You can look at Linux versus proprietary operating systems, or even going back to the roots of the classical computing industry. The machine that was built at Princeton, the IAS machine, they shared the plans for that pretty freely, and 8 or 9 or 10 different clones of that machine were replicated at Los Alamos Labs in I believe in Israel. Actually, I think there was one of either the Technion or somewhere in Israel. Anyway, right. And so, in contrast, the ENIAC, which was in service before the IAS machine, they tried to sort of own that IP and lock it down and be the exclusive holder of that technology, and it died out. There's no lineage of the ENIAC that exists beyond the life of that machine. Whereas the IAS machine, the architecture of that machine, even though it was realized in 1952, you can still see elements of modern computing in the way they architected that original machine. So my point is that the more open innovation around the IAS machine drove more innovation, more change, more advancement in classical computing than the closed project around ENIAC did. And we think the same is true now. I think it's always true, actually.
So if I get you correct, it's like a quantum readiness phase for you guys too, right? Because you
Absolutely.
Said it's not a revenue-driven model at this moment. So
that's right.
You're kind of experimenting with onboarding new partners, with collaborating with new vendors and new technologies and everything. So it goes for you too, right?
That's exactly right. Yeah, and as I mentioned, things like pricing models, those aren't set in stone. That's our best attempt to democratize access, and make it easier for customers to understand what they're going to pay for using a particular hardware device, and for hardware providers to understand what the model is for getting paid for using their devices. If there's a shift in the way those resources are presented or consumed that makes that model not make sense, we'll adjust that. Like, there's nothing, we don't believe that we've come up with the answer, any definitive answer around how this should work. It's all provisional, which fits very well, by the way, with AWS's larger culture. I've been really interested in joining, in sort of understanding the culture from the inside since joining in September. It really does have a culture of trying to get something out into the hands of customers and iterating, and not presuming that we've got the end answer right away. And you can see, again, back to EC2, with so much variation in the way EC2 is surfaced to customers now, with all those different types of chips, with EBS, so the different types of storage, S3, EBS, FSX. There's a number of different types of storage services that are attached to EC2. All of that is innovation that happened well after the launch of the service, which was it was just one type of processor, one type of image, one type of machine, and no attached storage at all when it first launched. So we expect the same kind of, actually more than that level of evolution in the quantum services as well.
Mm-hmm.
And I think if there's one other thing I would touch on, from the perspective of this is MIT Sloan. So from the perspective of entrepreneurial or investing, there's a lot of investment in the quantum space right now. There's a lot of startups in the quantum space right now. I think that the excitement is warranted. It also has very unique challenges in that I'm not aware of any other technology that has driven this level of investment at this earliest stage, right? Typically, with early stage technology investment, you're looking at something like a 3 to 5 year horizon for a return. or an exit. And that's not probably going to be the case for most quantum startups. There's no, in a way, we're in this kind of perfect black swan kind of environment. It might be that somebody has a breakthrough, before the end of this year that suddenly restructures the way the technology is seen and consumed, and suddenly there's some kind of quantum advantage. We all kind of line up behind that and off we go. It could take 10 years. We don't really know. And it's I say black swan because it's kind of, we can't tell what level of probability for the extreme positive or extreme negative kind of outcomes right now are. So it's a highly volatile, highly lots and lots of unknowns, but also as with any kind of very early stage technology with this much promise, there's also enormous opportunities. It just takes extra care and skill in sort of navigating this earliest stage technology, I think.
Any final question for Sebastian before we hit the end of the session? Yeah. Go ahead.
Yeah, Sebastian, in Amazon, like I understand, a lot of hardware guys are doing innovation and development. So, within AWS, what kind of innovation you guys are doing to make it successful?
Well, within the Center for Quantum Computing, where we're doing our hardware R&D, yeah. So it's a really interesting approach. They published a paper on the archive, I think January of last year, that described was a novel approach to error mitigation. So right now, the holy grail is error correction or error mitigation. These machines are noisy, and there's unlike classical bits where you can do things like measuring the bit with checksums and making sure that it's not flipping and getting an error. If you measure a qubit, it loses its value. So you can't do any more computation with it because it's decohering the quantum state. So error correction is very, very challenging. What the Center for Quantum Computing is trying to do is taking this approach called concatenated cat states. Cat states meaning they're Heisenbergian uncertainty states. So there's a trick they're using in quantum mechanics that makes a certain type of error much harder to occur, which limits the type of errors they need to correct for to phase flips and not bit flips, basically. So what they're doing is trying to implement that approach to error correction to build one logical qubit, so one error-corrected qubit with as many ancillary qubits as are needed for that one logical qubit to function with a lower error rate than is currently possible with an uncorrected NISQ qubit. So instead of, like, everyone else in the market has been trying to build qubits and scale up the number of qubits and simultaneously bring the noise down. The AWS team is trying to take a somewhat contrarian view and say, let's make one error-corrected qubit and then figure out how to scale beyond that afterwards. So that's where they're, and they've been, the center opened officially last October, but before that they were using Caltech, leasing Caltech space. So they've been working at it for a couple of years now. So I think, we should start to see some interesting early experimental results out of them in the near term.
Thank you.
Yeah, so
thank you.
We came to the end of this talk. So Sebastian, I really want to thank you very much. It was a pleasure having you here. I learned
My pleasure.
a lot.
Good.
And I want to thank everybody that joined us today and that will watch us later on. And I wish you all the best.
Thank you very much. Thanks, everybody. Thanks, Almo.
Bye-bye.
Take care.